Let's get started on private IP addressing, which is also known as NAT, Network Address Translation, and IPv6, IP version 6. But first, let's review what's meant by the IP 32-bit address space. An IP address, which is in an IP header, is made up of 32 bits. 32 bits are used to represent the IP address, 4 octets and 8 bits per octet. And this takes us to the limitations of IPv4. Since IP version 4 has 32-bit address space, how many IP addresses can we get out of that? And the answer is 2 to the power of 32. And that gives us a maximum of 4 billion IP addresses that can be derived from those 32 bits. And you might say 4 billion is a lot of IP addresses. But keep in mind, the population of the planet is 6.5 billion. And many people have several computers, each one of which has an IP address. And even Coke machines have IP addresses. So we are running out of IP addresses. The statement of the problem is that we are running out of IP addresses. So there are 2 potential solutions, both of which we will discuss. IP version 6 and private IP addressing, which is also known as NAT. Private IP addressing, which is also known as network address translation, is where many computers share one public IP address. So let's now review the difference between a public and a private IP address. When they first came out with TCP/IP, they only had public IP addresses, and that meant no 2 computers should have the same IP address, and that's the way it was for TCP/IP. But then they came along with private IP addresses, and private IP addresses are used within an organization, and many organizations can use the same internal IP address range. Private IP addresses are not globally unique. Private IP addressing, or NAT, is where many computers which have private IP addresses all share one public IP address. Here's the example: the Community College of Baltimore County and Howard Community College. Within CCBC, we use the IP address range of 10.0.0.0. And within Howard Community College, they use the same range of IP addresses. We use the same IP addresses within CCBC as they do at Howard Community College. So then, how can they connect to the internet? And the way they do that is all the computers within the organization connect to the internet by way of a single router, and that router is assigned the public IP address, and the public IP address must be globally unique. So at CCBC, before we had network address translation, every single computer had to have a public IP address, and that meant at the time we had to have 3,000 different public IP addresses, one for each computer at CCBC. But now, since we use private IP addresses internally, for the CCBC Catonsville campus, we only need one public IP address, and that is the IP address which is connected to the router, and that is the IP address which must be globally unique. This is an example of a large institution using network address translation, but we also see it used in small institutions. Here we can see that this computer has an IP address of 192.168.1.2, and the next one has an IP address of 192.168.1.3. This is a private IP address range. It's used at my home network, and it's used at your home wireless network. You and I are using the same IP addresses internally in our home networks. However, our cable modem, our wireless router, which connects us to the internet, it has an IP address as well, and that is a public IP address, and it is globally unique. So you can use NAT for large organizations and for small organizations. Large organizations tend to use a Class A IP network, such as 10.0.0.0 with a subnet mask of /8. That's used for large networks. And the IP address range 192.168.1.0 with a subnet mask of /24, which is a Class C IP address, is typically used for small networks, for small offices, and for home offices. Most wireless routers are typically pre-configured as DHCP servers, which issue the private IP address of 192.168.1.0 to all of the computers on that wireless network. In summary, network address translation, which is also known as private IP addressing, addresses the problem that we are running out of IP addresses. And with network address translations, many computers within an institution share one single public IP address. Now, let's discuss IPv6. The statement of the problem is that IPv4 has only a 32-bit address space, which only gives us 2 to the 32 potential host IDs, which is only 4 billion IP addresses, and that's just not enough to satisfy the needs of the Internet. So the two potential solutions are, one, network address translation, which we just discussed, or IPv6. Whereas IP version 4 has a 32-bit address space, IP version 6 has a 128-bit address space in the packet header. That's represented as 2 to the 128th. Or you could say that there are 340 trillion available IPv6 addresses. So that's enough that we could have an IP address for every single grain of rice in every single storehouse in the entire world. IPv6 gives us a lot of IP addresses. When we assign IP addresses, the tricky part is that it is written in hexadecimal. IPv4 is written in a dotted decimal notation, such as 192.168.10.100. But IPv6 is written in a hexadecimal notation because that is a really, really long number. Now, let's review hexadecimal. You already know what binary is. Let's talk about hex. Decimal 0 is represented as 0 in hex, so there's no difference there. 1 is represented as 1. 2 is represented as 2. 3, 4, 5, 6, 7, 8, 9. But in hexadecimal, 10 is represented as an A. 11 is represented as a B. 12 is represented as a C. 13 is represented as a D. 14 is represented as an E. And 15 is represented as an F. Why do they do this? Why do they make it so difficult? And the answer is, with hexadecimal, it allows you to use fewer characters to represent a larger number of values. That's why we use hex. So here's an example of an IP address, and it looks pretty long and painful, but if you look at it, you'll see that here is the network ID and here is the host ID. The network ID is F, which represents 15, and the host ID is A, which represents 10. Back up. 10 is represented as A in hex, and 15 is represented as F. So this would be network 15, workstation 10. Now, if you have a whole long string of zeros, that can be represented as simply a double colon to represent a whole long string of zeros. Saves you a little bit of writing. And furthermore, if you have leading zeros in each block of hexadecimal numbers, you can actually drop the leading zeros. So this is shorthand for network 15, workstation 10. Let's assign an IP address to a workstation. Let's take this workstation and assign that IP address 2001 1001:1009. So it's very similar to assigning an IP4 address. You go into Control Panel, into Network and Internet, and you go into Network Connections, and you don't click on IPv4, you select IPv6, and you click on Properties. And then we have to enter the IP address, the subnet mask, the default gateway, and the IP address of the DNS server, just like IPv4. So I type in the IPv6 address of this computer, which in this case would be 2001:1009. Then the subnet mask, which is a 64-bit subnet mask, the IP address of the default gateway, which usually ends in .1, and then the IP address of the DNS server. Then I click on OK and OK. Then to test it out, I go to the command prompt and I type ipconfig and I press the enter key. And now it shows that my IPv6 address, you can see it right here, is 2001:1001:1009. That is my IP address. If I want to ping myself, I can type ping followed by that IP address and press the enter key, and that allows me to ping myself. If I want to ping another computer, I type ping followed by the IPv6 address of that computer and press the enter key, and it tells me that I can ping that other computer. So you can see that ping works the same way in IPv4 and IPv6. It's just that with IPv6, the IP addresses are a lot longer and there's a lot more typing. Methods of assigning IP addresses. You can walk around to each individual computer and type in the IP address, or you can use the dynamic host configuration protocol, which we've already discussed. You can use the dynamic host configuration protocol with IPv6. So the DHCP client powers up and it sends a request to the DHCP server, which has a scope or a group of IP addresses. The DHCP server pushes the first available IP address down to the DHCP client, and now the DHCP client has an IP address. What if the DHCP server crashes? Well, similar to IPv4, auto-configuration kicks in. The workstation generates a self-generated IP address, and that is called a link local IP address. A self-generated IP address is called a link local IP address, and it always starts with FE80. So if you see a computer has an IPv6 address that begins with FE80, then that tells us it's a DHCP client that couldn't hit the DHCP server, so it's generated its own temporary IP address. So let's take a look. We go to the command prompt and we type ipconfig and press the enter key, and now we can see here is our link local IPv6 address, and it starts out with FE80. That's how we know it's a self-generated or a link local IPv6 address. So there are three ways by which an IPv6 workstation can get an IP address. You can manually type it in, you can use DHCP, or if the DHCP server fails, the workstation can generate its own temporary IP address. Many organizations are using both IPv4 and IPv6. So here's the question. If some servers in your organization are using IPv4 and some servers are using IPv6, then which version of IP should you have on your workstation? And the answer is both. You should have IPv6 enabled and IPv4 enabled, so you can talk to IPv4 servers and IPv6 servers. And they call this dual layer architecture, and they also call it dual stack architecture. In summary, in this section we saw that since IPv4 only has a 32-bit address space, you can only get 4 billion IP addresses out of IPv4. And there are two potential solutions. One, network address translation, where many computers share one public IP address, or in this section we discussed IPv6. IPv6 has a 128-bit IP address space, and that gives us 2 to the 128 potential IP addresses, which is 340 trillion IP addresses, which is plenty of IP addresses. And the only tricky part is that it is written in hexadecimal. And this concludes our section on IPv6 and NAT.